First of all, let me thank you, everybody, for attending this colloquium, and I'm welcoming you on behalf, let's say, of the Institute of Cosmos Sciences to the second colloquium of the year. And today, I'm particularly happy to have a speaker with Professor Gordon Baym, who has a long lifespan in physics. And let me just briefly mention some of the achievements he has done. By the way, I'm Bruno Julia Diaz from the Department of Structure and Constitution of Matter, and also from the Institute of Cosmos Sciences. So Gordon Baym is from the University of Urbana-Champaign, and he has been also affiliated to NORDITA for many years. He's a fantastically known theoretical physicist, American theoretical physicist, and has a large number of seminal papers on many branches on physics, ranging from condensed matter, from nuclear physics, and also astrophysics. So this, I will be very brief, but these very important or seminal contributions actually has earned them a number of prizes, notably the Hans Bethe Prize that he got in 2002 for understanding matter in extreme conditions, the Onsager Prize in 2008, so both of them very, very recent, for his contribution to quantum fluids, and lately the Eugene Finberg Medal in 2011 for his novel applications of quantum many-body theory to basically everything you can think of, so from nuclear physics to atomic physics to astrophysics and highly condensed matter physics. So Professor Baym is also a person who has made test books which were essentially very well known. So he made monographs on quantum mechanics and also on the statistical quantum mechanics, and has been basically also working on many, many aspects of theoretical physics. Just to also briefly say, well, I'm happy to have a speaker here who is not only knowledgeable, so to say, but he has been actually a participant of the physics of, let's say, the last century, to be a bit, maybe not the whole century, but a large part of it. Just to say, so Professor Baym graduated from Cornell. He did his master's at Harvard, and then he made his PhD in Harvard in 1960 under the supervision of Julian Springer. And since then, he has worked with people, like, let's say, with Hans Bethe himself, with Bardeen, with David Pines, with Mermin, with Jerry Brown, with Chris Pettick, Leo Kadanoff, and many more people. This is just a non-exhaustive list. So basically, it's a person who has witnessed many, many of the developments in theoretical physics in the last times. And basically, on today's colloquium, he will be his personal view on the recent developments in which extreme forms of matter have been produced, basically from the coldest to the hottest to the densest, actually, forms of matter in the universe. And without further delay, actually, I let the word to him. So thank you very much.
Well, thank you very much, Bruno. It's a pleasure to be back in Barcelona, seeing many old friends, meeting many new people. There's terrible resonance if you stand there. What I want to talk about today is new states of matter that people have discovered in the last 20 years or so. In particular, the two particular states of matter. One is the quark-gluon plasma, which can be made in ultrarelativistic heavy ion collisions, where you slam two big atomic nuclei together. I'll say more about that. And one reaches temperatures of about 100 MeV, which is equivalent to about 10 to the 12 degrees, either Celsius or Fahrenheit, it doesn't matter. It's also the temperature of the early universe right at the beginning, about a microsecond after the Big Bang. And as I'll stress later, it's also the material that one finds in the interiors of neutron stars. The second system I want to talk about a little bit are ultra-atomic systems, where since 1995, one has first trapped bosonic atoms producing very novel states of superfluidity, and more recently, BCS-type pairing among trapped fermion systems here. And the temperature ranges here, microkelvin to nanokelvin, and so these are certainly the coldest places in the universe. There may be colder ones somewhere if a more advanced lab exists in some distant star. But what's interesting about here is that there's some 10 to the 20 orders of magnitude in energy or temperature scales between these systems, yet there are some interesting deep relations between the two that I want to mention here. So just to remind you what quarks are, quarks come in three flavors, up, down, and strange. And there's also heavier quarks, charm, bottom, and top, which have a much more massive. They tend not to play much of a role in heavy ion collisions or in neutron stars. So just focus primarily on the up, down, and strange quarks here. Now, question, why should there be such a thing as quark matter? Well, certainly if you take ordinary matter and begin to compress it, one begins to form new states. If you take atoms and compress them, you go through, take sodium atoms, for example, and squeeze it together, you'll begin to form a metal. Eventually, you form a good plasma. And if you squeeze so far that all the electrons become dissociated from the nuclei, then one just has a plasma consisting of just atomic nuclei with electrons running through. And this happens, for example, in the outer layers of a neutron star. Now, on the other hand, if you take the atomic nuclei and begin to squeeze them together, you begin to form a state of nuclear matter here. Then the question, that nuclear matter has a density typically of around, well, 0.17 baryons per cubic Fermi, and a Fermi is 10 to the minus 13 centimeters. Or if you prefer using grams, 10 to the 14th grams per cubic centimeter. Now the question, what happens if you begin to squeeze the neutrons and protons even further? Now neutrons and protons are each made of 3 quarks, and if you squeeze that further, you begin to form what is called quark matter, in which you just have the individual quarks, the up and down quarks, and possibly strange quarks, just running uniformly through the system. This is sort of a picture of the state of matter in the universe from the Big Bang onward. And way back here, at times, about a microsecond after the Big Bang, matter was in the form of quark matter. And then eventually, at around a microsecond, it began to form nucleons, neutrons, protons. And then nuclei, eventually nuclei, stars, galaxies, people, eventually. All this matter plays a very interesting role in neutron stars as well. If you could read this, can anybody read what it says over there? Vaguely. Neutron stars are stars typically of about 1 to twice the mass of the sun, squeezed down to a radius of about 12 kilometers here. And so this is the densest matter in the universe. And with there's an outer crust in a neutron star, which is about 1 kilometer in width, consisting of atomic nuclei on the outside. Further in, one begins to form a sea of free neutrons here. As you go in to the center, after the nuclei begin to merge, one has free neutrons, protons, and electrons. But then in the inner core, it's always been a mystery what is there. And as I'll argue there, one begins to have uniform quark matter in the interior. How you get from here to here remains an interesting question, which I'll have things to say about. Now, one reason for mentioning cold atoms is that I think we're beginning to learn from cold atoms what some of the physics can be like in going from having nucleonic matter here to quark matter in the much deeper interior here. This is a phase diagram of what you expect matter to look like. Temperature vertically. This is measured in units of million electron volts, and baryon density horizontally. So nuclei sit here, and all the rest of physics sits way down in the lower pixel, all the way in this bottom pixel. All of solid state physics, chemistry, everything is way down there. The region up to around maybe 5 times nuclear matter density here is mostly hadronic. At much higher densities, one is just matter composed of quarks and gluons here. And similarly, as you heat the system, one has hadronic matter, and then at high enough temperature, high enough density, the matter becomes formed of quarks and gluons. At RHIC, the ultrarelativistic Hadron Collider at Brookhaven, and the LHC, one explores a regime around here. The early universe started very dense and comes down along here. FAIR, which is a machine being built at GSI in Darmstadt, will explore this regime over here. And neutron stars really ask what is going on at very, very low temperatures down here. Slightly different version of the same phase diagram, emphasizing the fact there's a critical point over here, and there's probably another critical point down here. And one of the interesting questions is how you go from the hadronic phase of neutrons, protons, to quarks at high density as you go through here. And what I want to argue is probably pretty continuous. Now, just a few properties of a quark-gluon plasmas. Quarks have color, three colors, red, blue, and green, or whatever your favorite colors are. They have, in addition, spin and half, particle, antiparticle, particles, antiparticles, and flavors go up, down, and strange. So that quark matter has many more degrees of freedom than ordinary nucleonic matter. And so what one finds is that at a given temperature, the entropy of quark matter will be much, much higher. Now, whether you have a sharp phase transition or just continuous, there still will be a large latent heat in going from quark matter down into ordinary nuclear matter here, if you plot entropy versus temperature. Now, at low temperature, very low temperature, quarks, because they're fermions, will form Fermi Cs. And so, for example, in a neutron star, you expect to have a Fermi Sea of up quarks and a Fermi Sea of down quarks, and slightly more of these because one has to charge balance between the two, basically. And in addition, one can have strange quarks, but fewer of these because strange quarks have a higher mass. Okay. Now, how do you begin to form quark matter? This was Sungdao Lee's, of Yang and Lee, his idea that you just collide nuclei as heavy as bulls, making forms of matter. This is a Japanese version of the same, sumo wrestling. And what really happens is this. Okay. One starts, there are three machines that produce quark matter. The Brookhaven machine, which we actually started in 1983. It took 17 years to get the first beams. And the beams have been running at 100 GeV per nucleon. These are collisions of gold on gold atoms here. At 100 nucleon per 100 GeV per nucleon. So this is hundreds times the rest mass in kinetic energy. The LHC has been going since 2010 and started again a few days ago, now with beams of 3,500 GeV per nucleon. So it's substantially higher. And FAIR will be running at much lower energy, about 4.45 GeV per nucleon. This is a layout of RIC. If you ever fly into Kennedy Airport in New York, you'll see this large circle from the sky. And to give you some idea, the beam is produced in a tandem Van de Graaff here, which is actually gone now, goes into the AGS, the alternating gradient synchrotron, accelerated and splits and bang the collision. So this is how the collider works. This is sort of a layout, and these are the beam lines, beams going opposite directions. What actually happens when you collide two atomic nuclei together? The theorist's view is very simple. What happens is the nuclei, these are gold or lead on lead. Lead is CERN and gold at Brookhaven. The nuclei, because they're going at completely relativistic velocities, they're very highly Lorentz contracted. So they would appear to be basically two pancakes. The two pancakes hit each other now and pass through each other because there's not really time enough for the nuclei, the outer regions here, to break up. But in between, one forms a very hot state of the vacuum, which is really the quark-gluon plasma here. And so here's a nice simple movie of how this works. So these are the nuclei. They're going to hit each other. And in the interior, then one begins to form lots of things, quarks and gluons. In particular, these rods that you see formed over here, these are basically strings, ordinary string theorists, QCD strings that are formed that eventually break up into individual quarks, and eventually they will form hadrons. Now, question is that was what it looks like to a theorist. What does it look like to an experimentalist? Well, it looks like that. What the experimentalist sees is in a detector of various kinds, lots of lines. And the problem is these are hadrons or electrons, muons. The problem is, how do you go from here? How do you go from this collection of tracks? How do you work back to actually discover the properties of the quark-gluon plasma? This is a very, very, very difficult job, which I have nothing to say about. Here's a picture of at Brookhaven, there are two major detectors, Phoenix and Star. These are every bit as big as the detectors at LHC. This is the canonical person over here, this whole gang of canonical people over here. And there were two smaller experiments that were done at Brookhaven, one called Brahms and Phobos, and those are closed. They're no longer functioning. At CERN, all the three detectors, ATLAS, CMS, and ALICE, can do heavy ions, but these CERN, the ALICE detector is devoted entirely to measuring heavy ion physics. And ALICE is very nice. It's an acronym that stands for a Large Ion Collider Experiment. It works very well here. And again, here's the person over here. So Alice has been taking data. This is, of course, Alice making a quark soup. Okay. So this is actually the first, one of the first events at Alice in 3.5 years ago. And again, you just see a lot of tracks. Now, I just wanted to say what are some of what has one learned from Rick and LHC experiments? It could be that the matter you made simply, that the nuclei just passed through each other, nothing interesting happened. But no, one begins to really form matter at very high energy density. This quark-gluon plasma really is formed. Energy densities are of order 5 GeV per cubic Fermi. This is on the order, an order of magnitude beyond the rest mass energy inside ordinary matter. The rest energy is just equals the mass times c squared is about 150 MeV, 0.15 GeV per cubic Fermi, and so one is 10 to 30 times that energy density here. So this matter that's been formed is really the most energetic matter ever made. Here, existed in the Big Bang, but not since then. So one has certainly produced a quark-gluon plasma, and it's a very nice quark-gluon plasma. It's very strongly interacting. One sees that, for example, if you have a collision, a so-called hard collision that produces two quarks at the side, one quark can go out, forms a jet of particles going this way. The other goes through the medium and gets broken up into a lot of fragments here. And so you get very lopsided jets produced, which give you some idea of what a jet does as it passes through the medium, how it breaks up, is an interesting way of probing what is going on inside the collision volume here. Now, because it's very strongly interacting, the pressure in the matter builds up very strongly, very rapidly. And as a consequence, to a very good approximation, one can describe the flow of the matter, how the collision evolves in terms of hydrodynamics. And that's led to some rather interesting results. In particular, although I won't have a chance to describe it, one finds that this matter has the smallest viscosity of any matter ever created here. There's an interesting dimensionless measure of the strength of viscosities, which you measure the viscosity divided by the entropy density. And this has units of simply h bar. And there's a fundamental bound that's been proven, not proven, demonstrated in string theory, that the viscosity in units of the entropy density should be bigger than 1/4 pi. At 0.08, this matter gets down to viscosity about 0.2 in those units. Water, on the other hand, has viscosity of about 100, so it's much more viscous. Okay, now I just want to give you some general idea of what has been done at RIC, but theoretically there are lots and lots of problems to be solved. In particular, we don't know how to solve QCD at all, quantum chromodynamics, at finite baryon density. The one insight one has into solving QCD, the one method is through lattice gauge theory. It's a very tremendously strongly interacting system through lattice gauge theory, but lattice gauge theory unfortunately fails for finite baryon density, something due to what is called the fermion sign problem, which you just need to know the words at the moment. And so one would like to be able to solve it and ask what does the phase diagram actually look like for hot and dense quark matter? For what regions does one explore in heavy ion collisions? What happens at low temperature if you try to form neutron stars out of such matter? what states do you go through? What is the equation of state as you start from ordinary neutrons and protons at low density through to quarks at high density? We don't know in detail. The many aspects of this that become important, there's pairing. Nucleons or quarks will pair to form color superconducting states. Chiral symmetry is broken. One has to have fairly stiff equations of state. It has to be able to support a lot of mass because, as I'll describe later, one has actually observed two neutron stars with masses of 2 solar masses. And so how do you make matter strong enough to support that much mass here? And of course, what is the role of strangeness in the equation of state? There are interesting dynamical problems, which I will not talk about at all. For example, how is the matter thermalized? What are the transport properties? Can you calculate the viscosity? For example, thermal conduction and such. In heavy ion collisions, what are the initial conditions like? There's some work on this, but it's still a very fuzzy area here. So even though you may have very good thermodynamics or some dynamical scheme, you don't really have a good sense of what are the initial conditions to apply as well here. So it remains a very, very fertile field for theorists. Okay, now let me switch gears down to very, very low energy and say just a very few words about cold atoms. One can trap bosons and fermions. Typically, one traps them in harmonic traps here. And the difference is that if you trap bosons at low enough temperature, they will all sink to the lowest state of the system and form a Bose condensate. A Bose condensate is characterized by one mode of the system having a macroscopic occupation. That means a fraction of the particles, a macroscopic fraction of the particles are in one state. Now, fermions, you can't do that. You're allowed to have one fermion per state. And so if you have two states, one likes to say spin up and spin down, but in cold atoms, one really does this with 2 different hyperfine states. Then one can, in fact, make BCS pairing among the systems here. And so one of the more interesting developments of the last 10 years has been producing degenerate Fermi gases and studying the states of pairing there. And the way one does experiments is pretty straightforward now. You start with a warm atomic vapor, typically room temperature about 1 million atoms per cubic centimeter. You put it in a trap, a magneto-optical trap, which quadrupole coils to trap the atoms magnetically. And then you apply laser cooling from all different directions. And laser cooling can cool a system down to about 50 microkelvin here. What happens in laser cooling is, of course, as an atom moves, it hits a laser, which slows it down. Now, that causes internal excitation of the atoms, and the atoms at some point will de-excite and recoil, and the recoil really sets the lowest temperature one can get to. Beyond that, one does evaporative cooling, and evaporative cooling is the standard way you go across your coffee cup to cool the coffee, and you blow away the hot coffee molecules, and you're left with cold coffee. Here, what you do is you remove all the hot molecules, but you do it with radio frequency techniques, and you're left with cold atoms. And atoms typically of order of 1 to 1,000 nanokelvin. This is from 1 nanokelvin to a microkelvin. Typical densities one gets are like 10 to the 14th, 10 to the 15th per cubic centimeter. But the trouble with evaporative cooling is you lose atoms, and so you end up with systems that are around 10 to the 5th, 10 to the 8th atoms only. This is just down the hall from my office in Urbana, Brian DeMarco's laboratory, which he set up the coldest place in Urbana-Champaign, less than 500 nanokelvin, but he's now changed to 2.1 nanokelvin here. What's amazing about this is there's no refrigerators. It's all done with lasers. You can get to these immensely low temperatures with lasers alone. Normally you think of lasers as being things you do heat with. You heat with, but here you cool. Another important difference, notice the size of the experimental apparatus here. This is all tabletop physics. I mean, this is the canonical human. here. This is somewhat larger. I mean, the actual trap is someplace right in here. Okay. Now, I mentioned there are similarities between these systems. There are a couple of obvious similarities. Both cold atoms and quark matter systems are typically of order 10 to the 4th, 10 to the 7th particles, small clouds with a lot of degrees of freedom here. Both are actually very strongly interacting systems. The quark-gluon plasma is always strongly interacting, as I'll describe in a moment. The atoms, one can, by simply changing magnetic fields through what is called Feshbach resonances, you can make the atoms strongly interacting as well. There are lots of different places where one can point to similarities. What I want to stress today is the question of the phase diagram of QCD, looking at similarities from the cold atom system and what one expects in quark-gluon plasmas here. I mentioned viscosity as another interesting connection. Fermi gases, cold atom Fermi gases, are also the other system in the world that has very, very low viscosity, about the same as strongly interacting quark matter here. There are interesting cold atom analogs of QCD in nuclear systems that give possibility of eventually simulating QCD using cold atom systems, but that's a generation away. The very wonderful game is producing artificial magnetic fields. I mean, you start with a collection of neutral particles, and for very clever techniques of applying lasers, you can convince the particles that they are really like charged particles moving in a magnetic field. So if you have an electron in a magnetic field, it will go around in a circle. And so here, through wonderful tricks of lasers, you can make the atoms think, neutral atoms think they are actually charged particles going around in circles here. That's a very exciting game. Because you can also make, in addition to magnetic fields, you can make non-abelian magnetic fields as well here. I won't say anything about physics of strongly interacting atomic plasmas, but they form very interesting analog systems where one can study plasma dynamics under dynamics of very, very strongly coupled plasmas here in the laboratory. And the interesting connection between superfluidity and pairing that one has between the trapped fermion systems and color superconductivity as one sees in neutron stars. Okay. Let me mention strong interaction. In quark-gluon plasmas, there's this famous formula for the strength of the interactions, similar to E squared over 4 pi in electrodynamics. One forms a strongly interacting coupling constant divided by 4 pi. And there's a formula over here in terms of the P is the momentum scale one's looking at. Lambda is a number, about 150 MeV. And what you see is as the typical energy increases from 1 to 10 to 100 GeV, the strength of the coupling keeps decreasing here, going down at this scale over here about 0.1. Now, this is always fairly large. No matter, one learns about asymptotic freedom, and if you go to high enough energy density or high enough scales, the matter becomes very strongly interacting. But it never really does that in real life. Even if you go down to the gut scale, this GS is about a half. And if you compare with electrodynamics, E squared over 4 pi is 1 over 137. In these units, E is about a third. So even at the gut scale, the grand unified scale, the interaction is still stronger than ordinary electrodynamics. And certainly in the region, at lower energy densities where one studies quark-gluon plasmas, one is in a much more strongly interacting regime here. So as far as we're concerned, the quark-gluon plasma is always a very strongly interacting system. And that is actually the reason why it has such a very low viscosity here. Now, if we look at atoms, the atoms at temperatures of a nanokelvin are moving very slowly. The hydrogen in the room is moving, what, 2 kilometers per second. If you could see it, it would be very fast. If you don't see it, it is very fast. Now, cool down to a nanokelvin. How fast does an atom move? It moves as fast as my fingertip is moving. The scale is millimeters per second, or even smaller. So then you ask, well, if take two such atoms, they collide. What is the typical angular momentum with which they collide? When they're close enough to feel the forces, they have to be very close, but they move incredibly slowly. So it's all really just zero angular momentum. The angular momentum is momentum times the arm, the length away, and the momentum is very, very tiny. And so it's really always in very low energy S states. Now, in very low energy S states, at very, very low energy, one can describe, as Fermi did, the interaction just by a simple pseudopotential, which is 4 pi h bar squared. A is the scattering, the atomic scattering length, which the cross section will be 4 pi a squared, divided by the atomic mass, times the delta function of r minus r prime. Just the interactions are effectively a contact interaction. Now, what's wonderful, however, is that with the magnetic field, as you see in this picture over here, in lithium-6, which is a fermion, one's at 843 Gauss, 830 Gauss, one can change the interaction, make it much stronger, and come out on the other side with an attractive interaction over here. This is this trick of Feshbach resonance, which that works. The way that works is very simple. Imagine you have two atoms scattering together in an S state. When they scatter, they will go into some other states. The hyperfine states can change. Total angular momentum is conserved, but the way the angular momentum in individual atom is apportioned to the nucleus and the electrons can change here. So in the scattering, generally the magnetic moment of in the intermediate state, the magnetic moment of the atoms, is different from the magnetic moment in the initial state, simply because the magnetic moment of atoms is due entirely to the electrons. The nuclear magnetic moments are down by a factor of 2,000. They're not important. And so what you see is that the magnetic moment in the intermediate state is different from that initial state. Now, if you apply a magnetic field to the system, the energy of the states become proportional to the magnetic moment times the magnetic field. And so you see an energy difference here between the two states that's proportional to the magnetic field times the difference of magnetic moment. And so by dialing the magnetic moment, one can make the energy denominator in the scattering amplitude vanish. If it vanishes, one has a scattering resonance, and that's the Feshbach resonance, simply. So you just dial the magnetic field to make the energy of the intermediate state the same as the initial state. And so you find a scattering length that has a general structure of some background, some constant divided by magnetic field minus a magnetic field of this Feshbach resonance here. Now, when you reach this magnetic field, what is really, it's not a situation where you suddenly get a very strong interaction and the system shakes. What has happened is the atomic phase shift has just become pi over 2, nothing more here. And so, but this is a picture here. As you pass through the resonance, the phase shift just goes through pi over 2. But it appears to be a very strongly interacting regime and a very interesting regime. At this magnetic field, which is resonance, one has what is called the unitary regime here. And it's a regime where the scattering length becomes very big, very much larger than the interparticle spacing. But the force range is always very small. Force range is measured in sort of nanometers at most. And so one is in a regime where the scattering length is far too large to be relevant because there are many particles. Scattering length describes two-particle physics. But there are many, many more particles involved in a distance scale of the scattering length. And so this is thoroughly irrelevant. The force range being tiny is irrelevant. One has a situation where the only scale in the problem is the interparticle spacing here. But so by making the interaction very strong here, one can make the matter very strongly interacting. And you see the difference very clearly if you look at lithium-7, which is a boson, versus lithium-6, which is a fermion. At 810 nanokelvin, these are really plots, atoms in a trap. And what you see here, the dark regions are basically the density of the particles. Now, as you cool down half a microkelvin, you see that the boson system is getting small, but the fermion system is remaining big. Go down to 240 nanokelvin. The fermion system still is big, but the Bose system is getting much more condensed. Why is the Fermi system remaining large? That's just ordinary statistics. You cannot put two fermions in the same place, and therefore there's an effect of repulsion. The system remains large. For the same reason that you don't fall through your seat now, even though there's lots of space. Just repulsion between your electrons and the electrons in the chair is keeping you up. Okay. Now, so by increasing the interactions via in this unitary regime over here near the resonance, one can get very high transition temperatures. In fact, one finds that the fermion systems will undergo BCS pairing at temperatures something like 2/10 of the degeneracy temperature of the Fermi temperature. These are the highest TC superconductors in the world here, even though the actual physical temperature is very, very low, but still measured in terms of fraction of the Fermi temperature, 20% is by far the highest TC materials that are known. Okay. Okay. Now I mentioned because of this lack of scale, both systems really are scale-free when they're strongly coupled. In the quark-gluon plasma, one finds that the free energy is proportional to the number of excitations, number of quarks and gluons and such, antiquarks, to the 4/3 power. It's a simple scaling. In cold atoms, you find the energy density goes the number of density to the 2/3 divided by the mass. This is precisely the formula for the energy density of a free Fermi gas. In fact, one can write the energy density as just the free Fermi gas result, which is this. The energy density is 3/5 of the Fermi energy, times a small correction. Now, calculating this correction, however, is a very, very difficult job, and there's no analytic way to calculate it. What one finds is that theoretically, this 1 plus beta is about 4/10. Beta is about -0.6. So the energy density is about 40% of the free Fermi gas energy. Experimentally, one finds exactly the same value here. And I just want to mention, just very briefly, this connection of the ultracold Fermi gases and low-density neutron matter. Calculation done by Gerzelis, my former student Joe Carlson here. This is looking at the Fermi momentum times A, and so this is very low density is here. And what you find is both in neutral matter and cold atoms, the energy densities really track each other perfectly as the system becomes denser. Eventually, the neutron matter is somewhat higher than the quark matter, and that's an effect that's due to the finite range of the nuclear forces. The cold atom forces are basically zero range on these scales, but the cold atoms, the nuclear forces have a finite range, which gives rise to what are called effective range effects here. So there's somewhat of a difference. But it's quite amazing how similar these look at low energy densities here. Okay. Now, let me come back to this crossover question, what the phase diagram looks like. I mentioned one of the exciting things was being able to make Cooper pairing of fermions. And here's a picture of what happens if you look at, this is showing as you increase the magnetic field here. So at very low magnetic fields down here, the lithium, this is lithium-6. Lithium-6 atoms will tend to form molecules, ordinary lithium-6 molecules, so effectively one spin up, one spin down here. Though in reality, in the experiments, these are two different hyperfine states. Now, as you increase the field, to go to very, very high field, to go through this Feshbach resonance, the interaction here is repulsive. This is the interaction strength. This is in scattering length versus magnetic field. This is the same picture of the resonance I showed you earlier. One goes through this crossover regime over here at the resonance. Now, what is happening in terms of the atoms is that very large magnetic field, one has a very weakly interacting system. One has transition temperature for superfluidity divided by the Fermi temperature, e to the -1 over the Fermi momentum times the scattering length here. Or this should be the magnitude of the scattering length. The atoms, the pairs are very large, as you see here, just like electrons in a metal. As you reduce the magnetic field, as you come lower here, the atoms, the pairs become smaller and smaller. In this intermediate regime over here, the pairs are basically the same size as the interparticle spacing here. When you go to much lower magnetic fields, then you won't begin to get very well-defined molecules here. But the important point is they're really, from one side to the other, is really completely continuous. To go from atomic molecules over here to BCS pairs. In fact, if you look at the early days of superconductivity in 1957, when BCS published their paper, there was a competing theory of superconductivity called Blatt, Butler, and Shafroth. Their theory was simply that electrons form tiny little molecules, and these tiny molecules would undergo BCS pair, undergo a BEC, Bose-Einstein condensation, and would form a superfluid. And that picture is actually completely correct. Though Bardeen would have nothing to do with this. He understood it, but he wanted to advertise how good BCS was, and so he said, no, you shouldn't look at that picture at all. But over the intervening years, it's been realized that, in fact, there really is a continuum here. And through cold atoms, one is able to study this transition experimentally, completely. You see, seen for the first time how BEC, from Bose-Einstein condensation to BCS superfluidity, is entirely continuum. As you pass through this pi over 2 over here, even though the scattering length is very big, the system doesn't undergo a phase transition. It's just, again, completely smooth. Yeah. Okay. This is the same picture again, only here I'm plotting temperature here. This is the transition temperature. So what is happening at very high magnetic fields, and it's very hot, the system has free fermions. One goes down and forms BCS pairs here. We form BCS pairs here. At very low magnetic fields, you start with free fermions that begin to form molecules, and then you get a Bose condensation of molecules. The transition temperature actually comes up a little bit. Calculating how it goes up a little bit is very hard, and then falls down to the BCS value over here. This intermediate regime, this is the unitary regime where the system is very, very strongly interacting and is scale free. Okay. And so you get this nice progression from tiny molecules to strongly interacting pairs whose distance is very comparable to interparticle spacing, to Cooper pairs whose size is very large compared to the interatomic spacing over here. Okay. Now, actually, in atomic clouds and nuclear matter, what I suspect is really a very similar kind of evolution of the quarks. In particular, the focus on down here, this is showing as the matter is getting denser at low temperature, nuclear matter, one starts with a neutron superfluid, goes through, maybe there's a little kink over here, but one begins to form pairs over here, and quite analogous to pairs over here, of quarks. These pairs are called the diquark system. They're just called diquarks. And so one kind of free quarks and diquarks. As one goes further into the system, one eventually forms a BCS paired system. What I want to propose is that the structure that you see in quark matter here, in neutron stars as you increase the density, is very, very similar to what one sees in the atomic systems over here. So one of the points I want to make is that I think the atomic systems have been a very nice guide to giving one insight into what can be happening in dense matter, of how one goes, how the matter manages to get deconfined over here. The problem is not completely solved at all. But in particular, this is again the same phase diagram: temperature versus chemical potential. I mentioned this tri-critical point over here. There's an additional crossover here, I believe, which I'll mention in a moment, which enables the system basically to go continuously from neutrons, protons, ordinary hadronic matter, to paired quarks, eventually to color superconducting states here. Okay. Now let me just say a word about why there should be such a crossover as this. There is quark matter. If you write down the Lagrangian and do all kinds of nice theoretical things, there's no scale in the problem. However, when you renormalize the system, it develops a scale. And in particular, there's also an extra symmetry called the U1 axial symmetry that disappears. It becomes spontaneously broken. And you see this, for example, if you look at the mass of the eta prime meson, which is very high and shouldn't be if there's this symmetry. Well, the details don't matter, but what happens is the breaking of the symmetry leads spontaneously to a 6-quark interaction, an attractive interaction between 6 quarks. And there's 6 quarks over here. Now, there are several ways that this interaction can take place. one can form a chiral condensate, which is essentially Q bar Q, which is like a particle-hole pairing in the system. And this gives rise to an attractive phi cubed interaction. But another important one it can do is if you look at the quark-quark pairing, like BCS pairs, one can get an interaction between d squared, d star, and the chiral symmetry breaking here. And that consequence is very nice. Because it's attractive, it says if you have a chiral condensate present here, if the system is chirally broken, it encourages formation of a pairing, quark pairing. Or if you have quark pairing, it encourages chiral condensation. The chiral symmetry breaking, the ordinary world is chiral symmetry. In the ordinary world, one has chiral symmetry breaking. At high densities in quark matter, one believes it goes away. But what it says here is that these encourage each other here. And so the system likes to have both chiral symmetry broken and quark pairing simultaneously. Details of this don't matter. But what happens is when it gets a phase diagram looking basically like this here. This is work I've done with Hatsuda and co-workers over the years, since 2006 here. That here's hadronic matter in which you have Q bar Q, which is the chiral condensate, basically quarks and antiquarks condensate, which you go through with some sort of transition here. We never figured out quite what this line is. But you still have a regime of Q bar Q not equal to 0 chiral condensate, and this sort of smoothly goes away. On the other hand, at high densities over here, one has color superconductivity, pairing of the quarks, and as you go through here, one still maintains pairing with the quarks. So what I want to look at is the question, as you come down here at low densities, which one has the neutron stars, how do you get from here to here? And here I want to propose this looks very similar to what one has in the atomic systems. Here. Okay. So this is the basic picture. As you go through here, hadrons out here, which are 3 particles paired together. One goes through the crossover regime over here where one has diquarks and quarks, and finally to ordinary BCS paired matter out here. And so that's the basic picture I want to have in mind here. Now, how you calculate is very hard because, as I said, we don't know how to calculate QCD at finite down here. QCD can be calculated over here, but down here one can basically guess. And so, but there's an interesting experimental laboratory. It's called neutron stars that begin to tell us a lot about what the equation state has to look like. And what I wanted to do is stress a little bit of that. So we look up at the stars now to learn what's going on. And what I wanted to stress is that some of these, what we're seeing is really, the observations there is really pushing our knowledge of nuclear theory to the edge here. Now, there are many ways that one can learn about neutron stars from observations. One is study masses. You simply, for example, you have 2 neutron stars and an ordinary star going around each other, and the stars are pulsing. You can measure Doppler shifts. And from the Doppler shifts, you can learn what the masses of the stars are. There are, in close binary systems, one can get mass going from one star onto the neutron star, which when mass gathers together, it eventually undergoes a thermonuclear burst, just explodes. And from that, you begin to learn knowledge of the radius of the star. And if you also know something about the mass, with mass versus radius information, that these are very strong, this produces very strong constraints on the equation of state of neutron stars. And so this masses versus radii here, just showing some of the constraints one has here. There are things called glitches, which are the slow, neutron stars slow down here. And then this is the Vela pulsar in 1969. Suddenly, boop, is sped up by 1 part in 10 to the 6th over here. This gives you information about what's going on in the outer layers, possibly stages of superfluidity in the crust. And then the cooling of neutron stars, where what you measure is a temperature versus time. This is 10 to the 6th years. Actually, you don't measure a temperature. What you measure is a luminosity. And you apply not good theory to say, that luminosity is just a hot black body. It's not a black body, and you don't know whether you're really seeing a star or a larger area or seeing a hot spot in the star. But nonetheless, there is information about how hot neutron stars are. But this is really a field much more for the future when we get much better understanding of how to go from observed luminosities to actual surface temperatures here. I want to focus on just this mass question over here. Now, observing a high mass neutron star is very important. It produces very strong constraints on the equation of state. In particular, if you have a very stiff equation of state, it allows a high mass. This is masses versus the density, central density. As the equation of state becomes softer, the maximum mass decreases. And so you can go to higher densities, but you can't support that much mass because the matter is just not strong enough here. And so what it says is if you find a neutron star, up here, then all these lower equations of state can be tossed out right away. Very simple criterion. Now, most neutron stars in binary orbits, neutron star orbits of systems, have masses about 1.4 solar masses. And that's probably an accident of how they got there. It's very hard to be able to take two ordinary stars, have each undergo a supernova explosion, leaving neutron stars without disrupting the orbit at all. You see, when the first star explodes, the second will just be blown away. But there are these systems of 1.4 solar mass binary stars. And that's consistent with the soft equation of state. There are a couple of other objects, heavier things, but in the past several years there have been some really nice measurements. These are basically neutron stars in close binary orbits with white dwarfs, who are really two solar masses to within 2% here. Now, these don't allow any softening. You really have to be way up there in very stiff equations of state. And there's a question, how do you make stiff equations of state to do this? This shows if you take nuclear models. This is looking at my colleague Vijay Pandeyappan and Jeff Ravenholm, a student many years ago, did the best nuclear matter calculation. You start out with neutrons, protons interacting via best nucleon-nucleon interaction you know, which is something like the argon-18. You add three-body forces, and this is mass versus central density, and you find the best you can do, depending upon, is something on the order of 2.2 to 2.4 solar masses. That's the maximum. And so you see, if you observe two, it's really pushing it. I mean, what happens when we next observe a 2.5 solar mass star? That could be. We don't know. It becomes a real challenge. The radius in these systems over here is typically on the order of 10 to the 12th Gauss. Sorry, not 10. It's about 12 kilometers. 12 kilometers. They have magnetic fields of 10 to 12 Gauss, but that's a whole different colloquium. Okay. Now, there are problems, however. You shouldn't believe this at all, even though it's wonderful work. Because if you look at densities, which is 5, 10 times nuclear matter density, the system cannot be described by ordinary nucleons because the nucleons are completely squeezed together here. I mean, it's like trying to study the properties of I'm going to say Swiss watches, Japanese watches, by putting them in a container and squeezing them down to a millionth their density. You learn nothing about what you knew about how watches work is completely irrelevant for that. Low densities, you could up to about twice nuclear matter density. It's okay. You could describe matter in terms of the force between nucleons. But when you go up, you can't use static two-body potentials or three-body potentials. All these systems, you have to put in two-body, three-body forces in order of stability. But there's no well-defined expansion. You need four-body forces, five-body forces. And the whole system really breaks down as you get to high enough densities here. And so I really just don't believe any equations of state based on nucleon-nucleon interactions alone at very high densities here. Now, here's some of these mass radius determinations that have been done. This is just, I showed a cartoon in this picture, but this is by Ferial Ozel. I haven't been part of this paper, but the actual detailed work was done by Ozel. And there's another paper by Latimer and company here, which applies different statistics, but basically the arguments are the same. Mass versus radius, so this is showing a mass of about 1.5 at someplace 10, 11 kilometers, and all rather similar. As of now, there are about 12 such objects for which one has mass radius determinations. Now, mass radius determination applies very strong constraints on equations of state. I'm just going to show you how to calculate this. I don't expect you to study this at all, but as I say, it's very hard to calculate quark matter because you cannot do you cannot do lattice gauge theory, and it's a strongly interacting system. So the best there are phenomenological theories like what's called the Nambu-Jono-Lasinho model, NJL, I should say someplace here, NJL, Nambu-Jono-Lasinho, which is an effective theory of quarks interacting, where one has gone a long way in fitting the parameters of this theory to known hadronic phenomenon. And what's interesting in here, you get up to 6 quark interactions. The 6 quark interactions are this effective Tuft interaction from the axial anomaly. Again, parameters one does not know very well. I want to focus on two parts of the interaction, even though it's hard to read. One is the effective pairing strength between quarks here. There's some canonical value there of the strength of this pairing H. And the other, which you don't have very good handle on, is an effective vector repulsion between quarks, as you would get from simple exchange of omega mesons here. Just in the same way that two charges repel each other, quarks will repel each other as well, but the actual strength is not well pinned down. And so we've been playing games, taking this and trying to look at varying the pairing strength and the vector repulsion to try and fit equations of state that are consistent with everything we know. And I'm almost done. Typical phase diagram here, again showing a critical point down here. Okay. Now, these are some of the results. In a very recent paper just published by postdoc Toru Kojo, well, one important feature among quarks is as you come down in density, quarks want to gather together and form two-body pair systems, BCS pairs or diquarks, and eventually form strong 3-body correlations. How do you get from 2-body correlations to 3-body correlations? 3-body correlations are the ordinary nucleons. And the way this probably happens, I like to think, is that you get diquark formation, 2-body objects, then the third quark is left over, and then at a certain point these will form nucleons here. And so it's a structure very similar, as I mentioned, to the very similar to the atomic gases, the atomic fermions, where you form molecules, and the molecules eventually go into pairs here. And so we've done calculations about that. One way you have to mimic that, though, is increase the strength of the ordinary pairing that one has beyond the standard Nambu-Jono-Lasinho value. And so we increase the strength of the pairing just for playing about 1.5 times what the standard result is. And also just play very strength of vector repulsions. What we find is very nice, that one can get up to well above two solar masses, family of neutron stars like this, of radii, something on the order of 10 to the 12, radii of order 12 kilometers here. These are very nice models of neutron stars. And what's really nice is, even though this is preliminary and from a paper a bunch of us are writing, which is, if you look, what is shown here is this region over here, the crosshatch region, is regime that Uzel figured out where the equation of state should lie to understand the masses versus radii. Latimer and company have a slightly different region over here. And what's very nice is the equations of state we're looking at are really going right through this over here. And so what we're beginning to get is I think, a very nice, consistent picture of what is going on inside neutron stars. That you start out with very early you start with nucleons, and nucleons will merge together to form diquarks. Diquarks eventually form BCS pairs and superconductivity. And one gets a very nice picture as you go all along. And so this, I would argue that one is really beginning to see a consistent picture of the inside of neutron stars. Namely, that the equation of state from hadrons to quarks is smooth. We can form very high mass neutron stars and also fit mass versus radius observations. Now, there's a very interesting problem with strange quarks, which I haven't mentioned, which is that if you look at the equations of state of using nucleons alone, you can get up to neutron stars of 2 solar masses. But that's without strange quarks. Now you begin to put in strange quarks, hyperons, lambdas, sigmas, and particles like that. And whenever you introduce more degrees of freedom, you lower the energy and you lower the pressure. And just like the ordinary variational principle in quantum mechanics. The more degrees of freedom you allow for, the lower the energy density be. And you find when you put in the best hyperons, the sigmas and lambdas, that the equation of state becomes too soft to support two solar mass stars. In quark matter, however, the strange quarks come in, but they come in as a Fermi C instead. And one ends up sufficiently stiff. And so what we really have is a consistent picture of high mass neutron stars with strange quarks. But I stress we're not there yet. This phrase is always when you take a trip with your children. They always sit in the back seat. You go 10 kilometers from home, and the children ask, "Are we there yet?" And the answer is no, we're not there yet. First of all, in going from nuclear matter to quark matter, the intermediate regime is still quite uncertain. One can do reasonable extrapolations between the two, interpolations, but there still are uncertainties there. And these will lead to errors in the maximum neutron masses and radii. We don't really know what the parameters are. We haven't solved QCD. And the trouble with the Nambu-Giannolassigno model is it doesn't include the gluons. The gluons are sort of integrated out, but the gluons are very important. In particular, gluons will produce what is called a bag constant, the energy density of just gluons in the vacuum here. And that's important for neutron stars because it affects the pressure. And the pressure affects the equation of state, and therefore the maximum solar mass. And so these are various things that need to be worked on much further. But I just want to indicate that I think we're really onto the right track here of how to produce dense cold matter to understand neutron stars. And neutron stars observations are a very important input to this as well, controlling. And a lot of the physics that's gone into this has been, not from heavy ion collisions, but also from understanding how transitions work in cold atom systems as well. So at this point, I will thank you very much and let you all go have lunch.
In some intuitive way, the relation between a very highly strongly interacting system and the low viscosity?
Yeah. I'll ask you a question. What is the viscosity of a very, very weakly interacting gas? The answer is huge. I mean, the viscosity is proportional to scattering times in kinetic theory. Scattering times are 1 over matrix elements squared. So the more strongly interacting a system is, the smaller the viscosity, or the more weakly interacting, the higher the viscosity. So for example, if you have viscosity just measures how well you can transfer momentum. So you have a stationary plate over here, fluid, and you move this like this. And you ask, if you move this, does this start to move? And that's just momentum being transferred along here. Now, if the system is very weakly interacting, an atom will hit here, move up very rapidly, hit here, and transfer momentum. So very large mean free path leads to very large viscosity. That's counterintuitive. You think things like oil should be high viscosity. It is high viscosity. But weakly interacting systems have even higher viscosities. Yeah. And so said the other way, the more strongly interacting a system is, the harder it is for the atoms to move. And so that leads to very, very low viscosity. And I mentioned the fact that both the quark systems in heavy ion collisions and also the atomic systems have very, very low viscosities. And you may ask, is this deep down because they have the same universality class or something? No. I think it's for the fact they're both the two of the most strongly interacting systems in the universe. Yeah. And that really is.
So you have mentioned that when you add new degrees of freedom to your system, usually the equation of state, it softens.
Softens, yes.
Then For instance, then when you add the exchange quarks, or when you want to accommodate these degrees of freedom to your picture, so in principle, that would be also new degrees of freedom, even if you add that at the level of free Fermi C.
Yes,
That should soften the equation of state.
absolutely right.
And then, so which is the ingredients that one should add in order to keep this higher, this high maximum mass of the neutron stars?
Yeah, that's a very nice question. As I said, when people put in hyperons, it softens the equation of state. But what people don't know how to put in is the interactions between the hyperons. You know, what you're doing really, we're populating Fermi Cs. And Fermi Cs, particles require to go to higher and higher momenta. And so there's really a lot, the Pauli principle is playing a big role, exclusion of states between particles. This must translate, as in ordinary nucleon interactions, where in short distances you have repulsion. This must translate into repulsive forces between the hyperons here. And so probably, and I'm going out on a limb here, I'll go stand at the edge here. As you begin, if you could put in hyperons with realistic forces, they probably would not lower the equation of state much, decrease the pressure much. Yeah. But, you know, because what it saves you is the fact that fermions and the degeneracy.
I just wanted to point to the last line of your last slide about gluons. And you had, you've been talking a lot about quarks and quark systems, so can you say something more about what is the role of gluons at high densities or maybe high magnetic fields?
Not very much. Again, if the gluons become gluons are what's called non-perturbative, meaning strongly interacting means you can't do perturbation theory. If they become more perturbative, more weakly interacting, that again would soften the equation of state, making it much more difficult to make high-mass neutron stars here. So it looks, from being just trying to be able to go smoothly from hadron equation of state to the quark equation of state, that the gluons must remain non-perturbative here. Now, in this very recent paper I mentioned, it's discussed in great detail there. But again, that remains an open problem, how this all works in detail. Yeah. QCD is a very hard problem. In fact, you know, that was a wonderful thing about switching to cold atoms. Heavy ion collision, you have to wait 20 years for data. Cold atoms, you get data in a week. You write a paper, it's published the next week. Completely different time scale.
I have a question actually on what do you think, I mean, people who are doing artificial gauge fields and are trying to link really to, let's say, to QCD eventually, what do you think about this approach? I mean, people are trying to understand about really strongly interacting theories where you have really artificial magnetic fields, even trying to make it, let's say, dynamical and things like that. Do you think this is a proper way to try to understand more things about QCD?
I think it's a wonderful way to understand strongly interacting systems altogether. I mean, yes, so certainly through the artificial gauge fields or simulated magnetic fields, one can produce things like artificial spin-orbit coupling, which leads to a system with a lot of physics you never imagined before. I mean, to do QCD is very hard. I mean, first of all, you want to be able to have, well, let me back up from QCD. In the artificial gauge fields, at the moment, all one can do is produce essentially a uniform fields. You can't change the field locally at all. That's far too difficult now. And furthermore, the systems are not polarizable. The particles, even though they react in the fields, they cannot produce a back reaction. How to do that is much more difficult. You know, there's something called Lenz's law. You know, if you put magnetic field on electrons, the electrons will produce a field that goes in the opposite direction. There is no, the atoms cannot produce fields themselves. There are ideas on how to do that, but that's really a crucial step here. And then the next thing you want to do is be able to make the magnetic fields, the system sort of more locally addressable. So you could say, what's the effect of applying a field here on the system over there? That's a long way down. Then to do QCD, you have to be able to develop fields with atoms which mimic the internal degrees of freedom, color, and such that you have flavors that you have in QCD. But it's not impossible. I mean, I think the speaker last week has been thinking about that.
Sirac is very much involved. Not last week, but previous colloquiums.
Last time, yeah.
So to say. Any more questions? If not, let me first say one thing is that at 3:30 we are organizing a gathering of master students, PhD students, and postdocs with Professor Baym at 3:30 in Aula Pere Pascual. And if anybody wants to come, please come at the end, or now, and tell me your name so that we have a rough idea of how many people are attending. And with that, I just would like to thank you again for your colloquium, and thank you everyone for